Tangent line approximations. This is something that we've done a lot of. So you should be pretty good at this. We've already done this. What we've done is said, for any curve that looks like that, at some point, we can choose some point, and for the immediate area, we can draw a line and get a linear equation that does a very good job of approximating that curve just in that area. And the equation for a line we know is y equals m x minus x1 plus y1 using point slope form. And the m that we're going to be using is the derivative at x1. So we're talking about, here's the point x1 and y1, and the slope of this line, the slope of that green line, is the derivative of my function at that point x sub 1. So here's my slope, x minus x1 plus y1. And this is written just slightly differently, but let's see how it really is the same thing. The local linearization, or the tangent line, local linearization and tangent line are the same thing. And what we've done is, instead of using x1, y1, we're saying let's choose the point A, and it corresponds to f of A. And the slope of this line, the slope, is the derivative of my function f prime evaluated at A. Same thing as we just did. And what it's saying is that for values close to A, my function is roughly, can roughly be, what's the word? Can roughly be described by this line, L of x, which is f of A plus, and this is my y value, plus f prime of A, my slope, x minus A, my x1. Same thing, where this is x1 and y1. Okay, so we're going to use this to do something called the Newton's method. But before we get into Newton's method, let's just, for the sake of confidence boosting, go in and see how well we know this local linearization already. So it says, find a tangent line approximation. Use the tangent line approximation of y equals root x at x equals 25 to find an approximate value of root 26. Wording's kind of strange, but let's just see how we do with this. Here's my function, root x. And what I want to do is find a tangent line approximation at x equals 25. So at x equals 25, we know that my corresponding y value, since y equals root x, is going to be 5. And we want to find a tangent line. And we're going to use that tangent line to approximate what my function is at 26. So to do that, first thing I need to do is find y prime. Well, we say y is, let's say y is x to the 1/2. It's helpful to write square roots as exponents. So y prime is going to be 1/2 x to the negative 1/2, which we could further simplify as 1 over 2 square root x. And we want to find this when x equals 25. So my derivative at 25 equals 1 over 2 times root 25, which is 1 over 10. Great. And I know that we're talking about the point 25 comma 5. So the linearization, the local linearization would be my y value. Well, I'm going to write it the way that I've been doing it. So the slope, which is 1 over 10, that's what we found here, times x minus 25, where this is my x value, plus my y value. That's the equation for a line. And well, let's just leave it like that. So then we want to approximate square root of 26. Well, because 26 is close to 25, my local linearization is going to do a good job at that approximation. So I can I can approximate, I can say root 26 is roughly L of 26, which equals 1/10 times 26 minus 25 plus 5, um, and that equals 5.1. So the question is, how well did this model work? Let's just take a quick check. If we open up our calculator and we find the square root of 26, ideally it's going to be close to 5.1, and in fact it is very close to 5.1. So our approximation worked pretty well. Let's do another one. So this is very similar to the problems that you're going to be doing in class the next day. So it says find the local linearization of the given function at the given input value a. Use the local linearization to predict the function's output value at a plus 1, and compare the predicted value to the actual value. Well, let's find the actual value first. Just working backwards. We want to find f of 3.3 plus 1, which is f of 4, which is 4 squared, 16. So our value should get close to 16. Okay, well, what do we need to do to get L of x? To get L of x, the first thing we need to do is find x and y. So x and y is, since we're looking at a3, we're talking about 3 f of 3, which is 3 comma 3 squared, or 3 comma 9. The next thing we need to do is find the slope. So to find the slope, we need to find f prime of x. Well, f prime of x equals 2x, taking the derivative of the function. And then we want to find the slope at the point x equals 3. So f prime of 3, which is 2 times 3, which equals 6. So my equation then is going to be y equals 6, x minus 3, plus 9. So if I now evaluate, and this is L of x. So if I evaluate L of x, and I want to evaluate it at 4 to see how well um, my approximation works. So L of 4, and we know that it should equal close to 16 because that's what f of 4 equals. So my approximation L of 4 is 6 plus 9, which is 15. Not as precise as before, but pretty close. Okay, so try this one on your own. And what I want you to do is pause the video, and when you've got a good answer, unpause it, and then I'll go through the solution. So first thing that we need to do is find a comma f of a, find the point. Well, the point 0 comma f of 0, which is 0 comma 1. So that's the point on the function, and the slope f prime of x. If we think about f of x as x plus 1 to the 1/2, you're probably becoming familiar with this. So the derivative is 1/2 times x plus 1 to the negative 1/2, and there's we can't differentiate anything inside there. That would just be 1. So the derivative is 1 over 2 times square root of x plus 1. And we want to find the derivative at 0. So that is 1 over 2 square root 1, which is just 1/2. So our linearization, we just found the slope, is the slope x minus 0 plus 1, or 1/2 x plus 1. And we want to use that linearization to predict, the function at a plus 1, or at 0 plus 1. So that would be 1/2 of 1 plus 1. So that's 1.5. That would be our approximation. And then we want to compare that to what it actually is. Well, what it actually is, f of 1 equals So square root of 1 plus 1, and that is 1.4 something. That's the square root of 2. I should know this. 1.47, 1.414, that's right. So 1.414. So we did, our linear approximation did a pretty good job at approximating the actual function. And of course, the local linearization works best. It's always going to work best when we're looking at values really, really close to our whatever our a value is. So if instead of looking at L of a plus 1, if we looked at L of a plus 0.1, it's going to be more accurate. Okay, I'm going to stop this video, and in the next video, we're going to look at how to use this local linearization to find zeros using Newton's method.